Okay, any question from this one? You can see you can or rather you need a couple of um, methods in the same problem, right? You need a bit of calculus. You also need a bit of algebra as well. So you need to combine these concepts all together, spatially, when you're trying to set that to zero and solve it, right? So you definitely need the concept. I'm repeating though, I did mention this yesterday as well, but that's what it is. Uh, if you are somehow struggling to find the zeros like this, that means set the equation to zero, set the expression to zero, and then solve it for a particular variable x, it would be in most cases. um, if you're somehow struggling to do that, please go back uh, to the materials of algebra, because you will need this for the rest of the semester. So if even if you know how to find the first derivative, um, if you just don't know how to find the zeros for this, then you'd be struggling to get to the result, right? So if you need help with this, I think you still have time uh, to go back and check your concept. There is no harm in in reviewing previous stuffs. Okay, and about the homework on 4.1, it's already posted. You'll see most of the questions will uh, find out your concept about uh, this type of problems. At least 3 or 4 problems will be just statements, no mathematics, no real calculation in that. If you have started it, you can already see uh, 3 or 4 questions are just statements of the things you will be doing, just to check your concept. Okay, and then uh, some graphical approach, and 2 or 3 algebraic approach as well. So I've tried to mix all these so that you can uh, see the output. Where are you standing right now with the concept, right? And obviously, it will help you um, uh, to grow in confidence before the exam if you're doing well, and vice versa. That means if you're not doing well, it will tell you that you need to practice some more. All right. Uh, any question from the slide 4.2? Because now we'll start 4.2, which is a very good theorem, and you will be using this obviously if you move forward with calculus in future. That means if you go to Calc 2, or even some other mathematical courses, you'll be using this particular theorem several times. Okay. Any question from the slides? Obviously, if you had enough time to go over this, anything you could generate when you just went over this? Okay. Um, before we start going over 4.2, 4.2, let's just first see this statement, Rolle's theorem, and we'll first see the statement and then go back to the graphical representation of it. Okay, let's see what the statement says. The statement says if if you have a function which is continuous on a closed interval and it's differentiable on that interval with the functional value equal to each other, functional values, I would say, equal to each other. That means if your endpoints are A and B, the functional value at A and the functional value at B will be equal to each other, okay? If that's the case, then you will have at least one point within that interval AB, let's say that's C, let's just say that's C. It could be anything, it could be any point, but at least one point within that interval for which your first derivative will be zero. That means if you evaluate your first derivative at that point, it will be zero. Now, what does that mean? Let's see the graph. So this is your function. And on this interval A and B, you could see your functional values are equal, right? It's f of A, it's f of B, and this dashed line actually gives us an idea that these values are equal. Your functional value at your endpoints are equal. Obviously, this function is continuous and differentiable in this, or rather on this interval, right? Because there is no hole, no break, we have defined values everywhere, and I can't see any corner points either. So looks like it's differentiable on this interval. We have the endpoints equal to each other. So what the Rolle's theorem saying is you'll have a value in this interval, let's say that C, where your first derivative will be zero. So in other words, what this is saying is you will have a point where if you draw a tangent line, it will be parallel to the x-axis like this. That means your first derivative at that point will be zero. Right? And why does it make sense? It actually makes sense because you can see for a certain interval, your functional values are equal. So that means even if you start from here, after a certain time, you will actually come back to this very place, because we said at the boundary points, your functional values have to be equal. So if you travel for some times like this, as my cursor is going, after a while, you will actually come back here at this very point. If your conditions are met like this, I mean, when the functional values are equal, right? And if the function is differentiable in that period, that means you'll definitely have a change of direction, but it will not be a corner point, because at the corner point, the derivative does not exist, right? We know that. But we said it is differentiable everywhere in that interval. So that means you will have the change of direction, but it will not be a corner point. And if that's the case, we already have seen this. If there is a change of direction like this, definitely at the peak point, that means at the highest point or at the lowest point, the derivative will be zero, right? And there could be more than one points like this. And that's what the theorem says. There is at least one point within that interval where your first derivative, if you evaluate that, evaluate your first derivative at that point, it will be zero. That means graphically, you will have a change of direction somewhere, maybe more than one, where if you draw a tangent line, it will be parallel to the x-axis. Do you agree? Just take your time, okay? Does it actually make sense? Take your time, okay? You don't need to memorize it. If you just understand what's going on, you don't need to memorize it. Any question from this? No questions at all? Very good. Let's see what we have next. So we have a couple of examples where the situation, or rather the requirements, the conditions are not met. And I think we have seen these examples before, like this one on our right. It is definitely continuous, but it's not really differentiable, right? Uh, Everywhere. It's not really differentiable everywhere, because at this point, it's not differentiable. It's a corner point. Or I would say, uh, even though there is a change of direction, you could see um, you could actually draw a tangent line here, um, which I guess would be vertical to the y-axis. Looks to me. Anyway, you can clearly eyeball that it's not differentiable, right? So our conditions are not met, because for Rolle's theorem to satisfy, to give us the point in between that, or rather on that interval, to find that value c, our function has to be differentiable everywhere on that interval. But it's not really interval here. It's not really a differentiable here, right? It's not differentiable here. And for this one, it's not even continuous. So there is no question of differentiability, because we know if it's not it's not continuous, it can't be differentiable there, right? We know that if the function is continuous on an interval, then we need more criteria to check whether it's differentiable or not. But if it's not continuous, then we don't need to say anything. It's never going to be differentiable everywhere on that interval, right? So this can't satisfy our requirements. So we can't really use the Rolle's theorem here. Do you agree? Everyone? Does it make sense?
Yeah.
Yeah, it seems pretty straightforward.
Very good. Okay. All right. Let's try this now. Okay, so we have this function, which I have actually picked up from this slide last time when I gave you this problem. I was actually scrolling up, to be honest, because it's actually in the opposite order. Anyway, I was scrolling up and I saw this problem, and I thought I should add this problem um, for your practice. Okay, so let's see if we can use the Rolle's theorem for this particular problem. So first of all, if we eyeball this uh, graph, we can see from 0 to 5, it's definitely differentiable, right? Because there is no hole There is no break, no corner points. Um, there is no horizontal, or rather, I would say the vertical tangent line or any other things that might create a point where it's not differentiable, but it's not the case. It is differentiable. It looks like it's differentiable everywhere, right? On this interval. Okay. Now, since it's differentiable on this interval from 0 to 5, we just need to see if there is any point where the derivative, the first derivative is 0. And again, as I said, if you see uh, a change of direction like this, or like this one, if you see any change of direction like this, what point means it was going up before the peak point, and it starts going down afterwards. That means if it's behave like this, you have a zero first derivative at the highest point or at the lowest point like this, or I would say at the change of direction like this. Okay, and you could see if we consider 0 to 5 on this interval, we have 2 points where the first derivative is 0. If you draw a tangent line here, if you draw a tangent line here, you will get a first derivative which is 0. And the Rolle's theorem said there is at least one point like that. And you can see we have actually 2, right? So that's why it said at least one point. That means it could be more than one, but there is at least one, right? And fortunately, we now know what these points are called. We have defined these points. Do you remember what's this? Anyone? What is this point? How can we define it?
You mean just like the maximum minimum?
No. Max, that's not the point, by the way. I mean, if we evaluate a derivative at a certain point, and if we get 0, how can we define that point? I mean, the point on the x-axis, not this one, not the functional value.
As a critical point?
Critical point, exactly. These values are actually our critical point, right? This 0.88 and 3.79, for which we are getting the first derivative 0, these are actually our critical points, right? Okay. Okay, now we'll see the statement of mean value theorem, and then we'll definitely see some graphical representation of it. And it's, as I said, it's really important, and we'll be using it in the mostly in the higher courses of mathematics. Not too much maybe in this course though, but it will be definitely using it. It's really important, and it definitely makes our life easier when we face or when we encounter harder problems. Okay, let's see what does it say. It says if a function is continuous on the closed interval and it's differentiable on the open interval, then there is at least one point on that interval or rather in that interval such that this ratio will give us the first derivative at that point. And what is this ratio? This ratio is, if you remember, we have seen this, we have seen something like this before, right? Where do you think we have seen this? Try to go back uh, to the starting week. You don't need to go to the slides. Just try to remember, where have you seen this? Only this left hand side, by the way. Try to remember, where have you seen this? Anyone?
Wasn't it when we were doing limits?
Um, we can actually go more precise. We have seen this. We have actually a definition like this.
That the secant line?
Exactly. Very good. We actually define the slope of the secant line as this, right? We picked up 2 points. We just subtracted the functional values and then took the ratio with the excuse me, with the change of variables itself, like this. It is actually the slope of the secant line. Very good, yeah. So the mean value theorem says this ratio will actually give us the first derivative at a point, and that point definitely lies in that interval. Okay, if you pick up an interval, um, if you pick up an interval, let's say A and B, and if you take the slope of the secant line there, okay, the slope of the secant line there, that means pick 2 points and add those. This will give you the slope of the secant line, right? So this will be the same as finding a point in that interval, let's say C, and get the first derivative at that point. That means we know the first derivative is actually the slope of the tangent line at that point, right? If you can draw a tangent line at a certain point, that slope of the tangent line will give us the first derivative at that point, right? We know that. So the mean value theorem says this slope of the tangent line and the slope of the secant line will be equal to each other. Obviously, you need to have more uh, conditions to see, conditions to cross check, which is your function has to be continuous and differentiable everywhere on this interval, and which is true. We can eyeball this graph and see this function is indeed differentiable, and obviously it's continuous everywhere on this interval, right? Now you might be wondering, why is that? I mean, why these two will give us the same result? How is that even possible? Can any guess why this could be true? Just eyeball the graph. All I'm saying is this graph, this straight line, the slope of the secant line, and this slope of the tangent line will be equal to each other, will give us the same result. Why do you think this is possible? You can see these lines are parallel to each other, right? Do you agree? These lines are actually parallel to each other. That means it has the same angle. If you try to reiterate like this, it creates the same angle with the x-axis. That means whatever this line is creating, this line is also creating the same angle. So the tangent of either of these angle, which are equal, to be honest, the tangent of that angle will be equal of those angles, right? And that's what um, the slope is all about. So since they're parallel to each other, their characteristics are same. They create the same angle, they go to the same direction, and uh, they will give you the same value simply because the tangent of either of this angle will be same. If you pick up any angle, uh, it's whether it's the uh, angle from the secant line or from the tangent line, you'll get the same result. That's why the slopes are equal. Any question from this? All of these are theoretical, though. There is no mathematical aspects as yet, but we'll see some definitely. But all of these are theoretical. So often it looks kind of bizarre, but when you go over this again and again, probably 2 or 3 times more, it starts to make more sense.
I actually did have a question on this.
Yeah.
So I don't know if I'm just like not understanding the theorem the right way, but how do we know like which points on the x-axis, like right now it's A and B, like how do we know which points to use that'll give us the same slope as the tangent line?
Okay, very good question. Yeah, very good question. How do you know? Because there are several points here, right? If you consider this interval AB, there are tons of points here which can be considered. So how do you know uh, uh, which point to pick? So for the Rolle's theorem, the answer is pretty straightforward. Just find the critical point. If you find the critical point, in most cases, if not all the cases, there will be some exceptional cases. Hopefully, we will not see those now because I guess we'll not be going that deep in this course. So if you find a critical point, you will get which point you should consider. But what about the mean value theorem? That's a good question. And the answer is, we'll see examples of it. I'll not reveal the answer now. Let's slowly go there, okay? Okay. Okay, let's see what we have for this function. 2x cubed minus 3x plus 1. That's the graph of this function. Okay, and if we pick 2 points on this graph, for the slope of the secant line, like this, we get the slope of the secant line is 5. Now, since it's continuous everywhere on this interval and it's differentiable, the mean value theorem says we'll have a point where, excuse me, where the slope of the tangent line will be equal to this. That means if we draw a tangent line on that point, the slope of that will be equal to the slope of this secant line. And you can see we have more than one, right? For this graph, although it's already worked out, we'll see how to do this a couple of minutes later. but we can see there could be more than one points like this where the slope of the tangent line could be equal to the slope of the secant line. So you might see a question like this, you know, a multiple choice question maybe, that I'll give you, or I would say, I'll give you a true false question like this. I'll have the statement that using the mean value theorem, we can find only one point for which the slope of the tangent line will be equal to the slope of the secant line. Is it true or false? You'll see questions like this. Okay, you might see, I shouldn't say you'll see, you might see a question like this. And it will be false, right? You can get more than one. So this could be a type of question. Or another type of question would be, I can give you a graph, although it's less likely, I generally don't do this, but it could be, I'll give you a graph like this. I'll draw a secant line and I'll ask you, where can you find, or can you locate a tangent line whose slope will be equal to the slope of the secant line? Okay, and you'll be given an answer box to type your solution. That means if you can locate a point, you just need to write that there. It's less likely though, I generally don't do that, but for the homework problem especially, you could see a problem like this. Okay. Okay. What else? Functions with equal derivatives. Zero derivative implies constant functions. Okay, so when we come back after the break, uh, instead of going for more theorems, I'll show one problem how to find this point uh, which will give you the same slope. Okay, so let's meet after 5 minutes, and meanwhile, obviously if you want to take a break, take a coffee break or something like that, go for that. But if you're staying here online, you can go over the statements of the mean value theorem again and try to digest what's going on. Okay, all right, let's meet at 10:05. Let's say my function is f of x. Oops, sorry. Let's take a really easy function, okay? Let's say x squared plus 2x, okay? And on the interval from 0 to 1. We're just trying to pick a really easy example because we're going to observe it for the first time. So I don't want to complicate things too much. Okay, and I'll have the theorem for you, which is the first derivative at some point c is equal to f of b minus f of a over b minus a, right? This is the theorem. Okay, now the question could be how to find a c in between this interval, right? We are looking for a value between 0 and 1 for which this will be true. Now, we can actually eyeball, or rather use the theorem to find out the value of C. How? Okay, so first of all, we want to get the left-hand side. Let's find out the left-hand side, okay? So what's the first derivative? That's the first question. What's the first derivative? The first derivative is 2x plus 2, right? 2x plus 2. And we want to have f prime of c. What's f prime of c? It will be 2c plus 2. That's our left-hand side. Any question from this before we go to the right-hand side? Since we are evaluating the first derivative at that point, that means we need to find the first derivative and then plug in c in place of x. Do you agree? Okay, the second job is to find the right-hand side. Okay, let's do that. So f of b, oops, sorry. F of b minus f of a over b minus a, right? And we know for our problem b is 1 and a is 0, right? So we need to plug in 1 in place of this function, this x first, and then subtract by plugging in 0 in place of x. So if we plug in 1 in place of this x, we get 1 squared plus 2 times 1, which is 3, minus, if we plug in 0 in place of x, it will give us 0. And b is 1, a is 0, so 1 minus 0. So it will be 3. Do you agree? Any question from the right-hand side? I mean, what did I do or how did I do?
Oh wait, sorry. How did you get 3?
So what's your b here? For f of b, what's your b for this problem?
Isn't it, well, x squared plus 2x plus 0, so wouldn't it be 2?
No, your ab comes from here, the interval.
Oh, yeah.
The b is 1. So you just need to plug in 1 in place of the x's you have for f of b. Just find the functional value of that. So this is literally, okay, let me rewrite it for you. This is actually f of 1 minus f of 0. And f of 1 is 3, f of 0 is 0. So you get 3 minus 0, which is 3.
Oh, duh. Yeah. All right. Thanks.
No problem. Okay, now we are almost done. We know that this left-hand side and this right-hand side are equal, right? Using this MPT, that means mean value theorem. So you can set this to equal, that is 2c plus 2 equals to 3. And now we can easily solve it for c. to get our desired result. So as you can see, if we know the formula, I would say the theorem, the mean value theorem, we can actually easily calculate C from it, algebraically, of course. What could be the graphical approach? Well, if you can draw a parallel line to that secant line at any point, obviously it has to be a tangent line at that point, then you're done. But for the algebraic approach, you just follow the formula, the theorem, what the theorem or the statement of the theorem says. So if we solve it for C, we get 2C equals to 1. That means C is half. So that's it. That's your C for this problem. Any question from this? Take your time, okay? No questions at all? Let me give you a problem. And again, I want you to work in pairs. Today I'll make a group of 2 and I'll ask questions from each of you, okay? How to do that or how do you do that? If you can't do, no worries, but you have to try at least. Even if it's wrong, doesn't matter as long as you try, okay? So let me give you a problem and then uh, assign groups for it. Okay, so one, two, three. Okay, I've created 5 groups. And here you go. And I'm going to write the equation for you. Okay, let us solve it and see if we can generate a question from it. So the first question is, what's the first thing we need to do here?
You need to find the derivative of the function. So if you put the 3 in front, it'll be 3x, and then you lower the power to x squared. So it'll be 3x squared minus 3, and then you get rid of the 10.
Okay. Okay, now what's the next thing? Someone else? What's the next thing we need to do? And someone
After
else?
that, I use the f of b minus f of a over b minus a equation.
Are we done with this part?
I use that after I
Oh,
use that equation I just said, but
okay, so what did you get for the right hand side?
so after I did or put all the numbers in, I just got 6.
Okay.
It was yeah, f of 3 minus f of 0 over 3 minus 0.
Okay, so is there anyone who can verify whether we'll actually get 6 or not? I mean, if you have a different result, please share with us.
We got 6.
Okay, very good. So let's see. I want to show the work as well. So if we plug in 3 here, we get 3 cubed, which is 27, minus 3 times 3, which is 9, plus 10. So it's 17, sorry, 18 plus 10, which is 28, really? Did I get it wrong? 27 minus 9 plus 10, it's 28, yeah. Or am I doing it wrong? I don't see it. We are getting 6 here. Am I doing it wrong?
I got 28, and then it's the f of, you have to minus f of a, which is just 10. And then
Oh,
that's
sorry, yeah, I got it, yeah. I forgot this part. Yeah, thank you. Right. So yeah, 28 minus f of 0. So this will be 0, this will be 0. We'll have only 10, yeah. So we'll have minus 10 over 3, which is 6, yeah, thank you. Okay, now what's next? Someone else. What should we do next?
You're going to put the 3c squared minus 3 equal to 6 and solve.
So this, I guess this should be done here so that you don't make a mistake. So 3c squared minus 3, and then we just need to set this equal to 6. Okay, now if we solve it, 3c squared will be 9, c squared will be 3, c will be plus minus 3. Do you agree? Or is there more we can do here? Let me show the question, entire question here. Can we do more?
It can't be minus 3 because it's not in the actual interval.
Very good. Excellent. It gives us a negative square root of 3 and a positive square root of 3. But we know this c has to be in the interval, right? This has to be in the interval. And the interval is from 0 to 3. There is no way we can have a negative square root of 3. Very good. So our answer is this. Now, any question from this? Any question from this? Anyone? Any question? No questions at all?
I have just a clarifying question. So when we plug the numbers in, we use the original function or the differentiated function?
I couldn't understand. Would you please say just a little bit louder, maybe?
Yeah. So when you plugged in like the 3, we use the original function?
Yeah, of course.
Okay. Okay, thank you.
Because if you see the definition, it's not the derivative, right? It's the original function. Yeah, good question though, because it's often quite confusing. Because on your left, you are doing it with the derivative. On your right, you're doing it with the functional value, original function, right? Okay. If you don't have any other question, we can move to the next topic, whichever we have next. No questions at all? Okay. Let's move on then and see if we can find a new and yet we have the zero derivative implies constant function. Okay, now that's really pretty intuitive, and I'll show why, or rather how. So if you remember, first of all, let me state the theorem for you. So the theorem 4.5 at slide 11 for 4.2 says if your function f is differentiable and f prime x is 0 for all points, that means if you find the derivative, it will always be 0 at any point for the interval. Then for that, or I mean on that interval, your function e is a constant function. And it makes sense because if you remember, if we have a constant here, whatever it is, the first derivative of any constant is 0. Do you agree? And that's what the theorem says, in the reversed order, of course. We know that if we have a constant, the derivative of that constant will be 0. The theorem says if your derivative is 0 everywhere on an interval, then obviously the function is constant. Does it make sense? We have already seen this, right? But in the reversed order. No questions at all? Okay. Let's see what we have next. Oh, yeah. Okay, so two of you have emailed me about not finding the recording. I don't know if there is any technical issues with that, but the link I provided should uh, have all the recordings, afterwards. Obviously I have uploaded videos up to a certain date, and then actually we ran short of uh, space on Canvas. That's why I needed to upload the recordings on OneDrive, and I've actually shared the links in the announcements. So I don't know why it's not accessible. It should be. I'll check on that whether if there is anything from my part. But can anyone else see the videos?
I've been able to.
Okay, that's good.
I've
Yeah.
been able to. I also had another class run out of space on Canvas, and they like requested more space and got it.
Oh, okay, yeah. Okay, that's a good suggestion. Yeah, I think I can do that. That would be nice, yeah. Because if all the recordings are at the same place, it would be easier for you to navigate all those. Yeah, yeah, that's a good Good thing to know. I'll definitely request for more space today. Thank you for that. Okay. Because this is the first time I have experienced this, to be honest, because these videos are too big, almost 2 hours recordings each day. That's why we have actually run short of memory, because generally, from my previous experience, we have lots of space left even after a regular semester. But yeah, hopefully this is the last one online. UW is going to start in person, face-to-face lectures from this fall. So hopefully things will be much better. All right, so let's see what we have next. Okay, we'll now start slide 4.3. And if you have the slides, it will start on, it will start at page 95 of that big slide I gave you a couple of days back. So 4.3. Okay, let me start sharing the screen, because now we'll just discuss some graphical approach. So let me start sharing the screen again. Okay. So 4.3, what derivatives tell us? Okay, let's see if we can find out what derivatives rather tell us. Okay, so first of all, we want to know this definition, which is pretty intuitive. Again, we want to know where the function is increasing, where the function is decreasing, and obviously, if you have a function which is, the functional value is greater than the functional value of some other points, when you are moving to your right, if your value which you pick up, let's say if you pick up x1 and x2, x2 is greater than x1, and if the functional value at x2 is also greater than the functional value at x1, like this, then we say that this function is definitely increasing. Okay. And if the functional value is decreasing, that means even though x2 is greater than x1, whichever you pick, even though x2 is greater than x1, your functional value at x2 is actually less than the functional value at x1, like this, then we say the function is decreasing. Again, this is just the definition. If you see the graph, hopefully you will understand it better. So let's see the graph, and then if we need, we'll come back to it. We'll come back to the definitions again. Okay. So let's see this graph on our left first. Let's pick up 2 points, x1 and x2. And clearly, this x2 is greater than this x1 because we are going to our right on the x-axis, right? So this x2 is definitely bigger than x1. And if we eyeball the graph, we could see the functional value at x2 is at a higher position than the functional value of x1. It's going up, right? It's quite easy to eyeball it from the graph. The function is going up. As we are moving to our right, the function is also going up. That means it's definitely increasing on this interval, right? And if we eyeball the graph on our right, you could see as we are going to our right, the function is slowly and slowly going downwards, right? You could see the functional value at x2 is definitely at a lower position than the functional value at x1. Do you agree? And if that's the case, even if you don't know the definition, if I ask you whether the function is increasing or decreasing, all 11 of you will straight away say it's decreasing, right? So it's really easy to eyeball it from the graph. But you can always check with the definition as well. And it will help us to find the algebraic approach later, tomorrow maybe, if not today. Okay, now let's see what else can we derive from it. So when the function is increasing at a certain interval, you could see if you draw tangent lines on any point on that increasing part of the function, you will see the slope of the tangent will be positive. Can you see this? This is the increasing part, right? This is the increasing part. If you draw a tangent line here, at any point, you will see the slope will be positive. That means if you can join the tangent line with the x-axis, you will see it's creating an angle less than 90 degrees. That means the slopes will be positive. And vice versa for the decreasing part. If you draw a tangent line here, at any point, you will see the slopes will be negative, right? You can just join it with the x-axis and you will see the angle is more than 90 degrees for any angle, for a tangent line anywhere on this decreasing part. So that's what we can always remember. Let me show you the algebraic part of it. Yeah. So if you have a differentiable function, I mean, if a function is differentiable at an interval or on an interval, I would say, and if the first derivative is 0 everywhere on that interval, then it's increasing. And if the first derivative is decreasing, or I would say less than 0, I should say negative, if the first derivative is less than 0 or at any point on that interval, then we say the function is decreasing. This is just what we have seen here. Okay, and this is the algebraic approach for it. Now, what does this mean? This means if I give you a function and if I ask you, for a certain interval, find whether the function is decreasing or increasing, all you need to do, all you need to do is to find the first derivative and check whether the first derivative is greater than 0 or less than 0 on that interval. That's it. If it's positive, I mean it's greater than 0, then you can say that the function is increasing on that interval. And if it's less than 0 or it's negative, then we can conclude that the function is decreasing on that interval. Any question from this? No questions at all? Okay. Let's see this graph and see if we can generate more information from it. And if you have any question in between, just write in the chat or wait for me to stop or take a break. When I take a pause, then ask the question, okay? Don't hesitate if you have any question. Okay, let's see this graph. This is quite an interesting graph because you can see there is some behaviors we have seen on separate graphs, but we can see this as a combination of all these behaviors on the same graph. Like this one, there is a change of direction here, but it's not really going up, changing direction. It's actually, I shouldn't say change of direction. You can see it's taking a slight turn over here and then starts going down again. We've seen a graph like this, I guess, for x cubed or something like that, a couple of lectures back. And then we can see a certain change of direction here. And we can see a change of direction here as well, but with a corner point assigned to the peak point. I mean, with a corner point at the peak. So there are so many behaviors on the same graph. That's a good thing. We can actually combine all our concepts together. Okay, let's see what we can do here. All right, so let's start from our left. If we pick up this interval from 0 to, let's say, -4, this looks like -4 to me. So from 0 to -4, you can see the graph is definitely going up, right? And if you draw a tangent line at any point, okay, you will see it creates an angle less than 90 degrees with the x-axis. That means our first derivative is also positive, right? And definitely it also signifies that our function is increasing on that interval, right? Okay, what happens at x equals 0? This is our x equals 0 line. At x equals 0, we can see there is a corner point, right? The graph is changing its direction, but it's a corner point. And at a corner point, we know the function is not differentiable. So the derivative at 0 is undefined. Do you agree? Okay. Next, from 0 to +4 now. If you can draw a tangent line at any point here on this part from 0 to 4, you will see it creates an angle with the x-axis more than 90 degrees. Okay, it creates an angle of more than 90 degrees. If you try to draw a tangent line anywhere at any point on this part of the graph. So that means it's decreasing, and obviously we can eyeball it as well. The function is going down, right? at any point, the functional value is lower than the previous point, right? All right. Now what happens at 4 precisely, at x equals 4? Okay, now we can see if we draw a tangent line at x equals 4, it goes parallel to the x-axis. Or in other words, we can see that it has a local minimum at x equals 4. Do you agree? If I say we have a local minimum here, do you agree with that? And at the minimum point, definitely the derivative is going to be 0, right? Obviously, if the case is like this, if it's not the end point. So at 4, our derivative is 0. Let's see the next interval, which is from 4 to 6. And again, if we draw a tangent line anywhere on this graph, anywhere, you'll see that the derivative, the slope of the tangent line will be positive. That means the derivative will be positive. And even we can eyeball it, right? It's going up and up. So it's definitely increasing on this interval. Same goes for from 6 to 8. You can see the graph is increasing, right? What happens at 6? Again, if we draw a tangent line at 6, we'll be able to see that it goes parallel to the x-axis. That means at 6, the first derivative will be 0. Whenever you can draw a tangent line at a point which goes exactly parallel to the x-axis, you can always say that at that point, our derivative will be 0. Okay? Now, you can see on a single graph, we can find several behavioral aspects. The function could, I mean, the first derivative could be positive, it could be 0, it could be negative, right? Or it could be vertical to the x-axis, or in other words, undefined, right? So you might see a question where I'll give you a graph like this, and for certain intervals, I'll ask questions like this. For example, I'll ask, from this graph, tell me what happens in the interval 0 to 4. And you will be given options like the first derivative is 0, the first derivative is undefined, the first derivative is increasing, the first derivative is decreasing. You will have 4 options like this, and you need to pick up the right one just by eyeballing the graph. Any question from this? I guess you will definitely see a question like this in the homework at least. Okay, I'll give you a graph like this, and I'll give you a certain interval, and I'll ask you what is happening here. Just tell me the behavior on this interval. Any question from this? Anything that is not clear to you? All good? Let's see another graph then. So let's say we have this graph. Oops, we have tons of more graphs. That's cool. All right. Let's say we have this graph. And again, let's say I am giving you this graph in black, which is for x e to the negative x, okay? And again, I'll be giving you this interval. For example, I'll say, tell me the behavior of this function x e to the minus x for the interval -1 to 1, okay? And you can see the graph is increasing on this part, right? For this graph, for this function, obviously, you can see it's definitely increasing, right? And if I say from +1 to +3, you can see the function is definitely, I mean, the graph is definitely going downwards. Now, how can you verify algebraically? So if you remember, to do this algebraically, we just need to find the first derivative and see within that interval whether the function is increasing. I mean, whether I should say whether the function is positive or negative. That's it. So without eyeballing the solution, can you tell me the derivative of this x times e to the negative x? Don't look at the solution. And first of all, can you tell me how to find the derivative of this? That would be the first question, I guess. When you eyeball a problem like this, x e to the negative x, and if I say find the derivative of it, what's the first thing comes into your mind? How to do this? How to find the derivative of this? Anyone? Just give it a try. Which formula should we use at least? No one at all? Just give it a try. Or if anyone trying to say something, I should check. Often the audio doesn't work. Who wants to give it a try? Okay, let me ask you from the participants list, because I need to have answers for this, because if you don't know how to find the derivative of this, then there is no way you can solve it algebraically, right? Yeah, Matthew, are you trying to say something?
Yeah, I got x e to the negative x minus e to the negative x.
Okay, so that's the solution. But my question is, what should you do in the first place? I mean, if you see a problem like this, what's
Product
the
rule.
Product rule, very good, exactly. It's the product of two functions, so we have to go for the product rule. That means we keep one function and find the derivative of the other, and we keep doing it until we find the derivative of all the functions. So if we keep x, what's the derivative of e to the negative x? Anyone other than Matthew? What's the derivative of e to the negative x? We have done this tons of times, at least 5 times, if not more. The derivative of it, e to the negative x.
Is it negative e to the negative x?
I can't hear you.
Sorry, is it negative e to the negative x?
Very good, exactly. It's negative e to the negative x. Okay, so if we keep x, we have x times, or I would say negative x times e to the negative x. Now, if we keep e to the negative x, what's the derivative of x? Someone else other than Ada and Matthew?
Just one.
One, exactly. That's the easiest of those. So the combined derivative will look like this, right? 1 minus x times e to the negative x. Okay, now we have found out the derivative. That's pretty good. The next job is to check for a certain interval whether we have a positive value or a negative value. So if I tell you from -1 to 1, you just need to plug in values. Let's try -1, then 0, then 1. Try these values, at least 2 or 3 different values from the entire interval, if not more. Plug in these values in place of this x, and if you do that, you will see you'll get a positive value if you pick any value from this -1 to 1 for this derivative. Whichever value you pick from -1 to 1, if you plug it in here, you'll always get a positive value for this first derivative. Don't trust me, do it, okay? Once we are done, if you have enough time today, if you are not working, just plug in a couple of values from this interval on this derivative and check whether you get a positive value or not, okay? And same goes for this interval. If you plug in any value from +1 to 3 on this first derivative, you will get a negative value. You'll get a value less than 0, okay? And cross-check it, don't trust me, okay? Cross-check it and see if you actually get it or not. I'll probably not give you a question like this, at least in the exam, because for this, if you just plug in one value from a certain interval and get a positive value, you can't really conclude, if you don't have the graph, of course, if you are just given the function, and if you just plug in one value in the first derivative and get a positive value, you can't guarantee that the function will be increasing, okay? Because it might be changing direction somewhere for some other functions. You never know. So the algebraic approach is quite time consuming if you do like this. We'll have better approach, although in the next lecture, hopefully. But I'll definitely not give you a question like this in the exam. But for the homework, you might see one. So definitely you should cross-check this once we're done with this lecture. Okay. All right, so we'll continue from this graph next time, I mean tomorrow. And obviously, before we meet tomorrow, I want you guys to go over the slide 4.3. Okay, and if you can generate questions from this, that would be even better. Okay, any question from today's discussion? Anything that is still confusing?